Oh, fantastic. Okay, so it's a pleasure to introduce the next speaker, Rahul Jain from USC, a Berkeley grad of some years back, and well known in stochastic systems and optimization, and more recently, well, actually, quite a well known in reinforcement learning. We became buddies at the Simons program 2 years ago, and I'll just let you go, Rahul.
Sean, thank you very much for the kind introduction, and thank you to you, Mengdi and Emma, for organizing this very interesting workshop. So it's a hard act to follow after excellent talks by Munzer and Alex, but I will try my best. And the flavor of this talk is slightly different from the first two talks. So I'm going to talk about reinforcement learning for continuous state and action space systems using generative models. And it's only a 25-minute talk, so I thought I'll focus on something very specific, a specific problem. This is work this builds on work that I've been doing earlier. I've presented before at Simons. This joint work with Hiteshi, but like I was saying, it builds on prior work. And I guess it's good to acknowledge the work with former students and postdocs and other collaborators with whom that happened. Okay, so let me start by just stating the obvious. I think we've all heard of the various successes of reinforcement learning, particularly deep reinforcement learning on various kinds of games in particular. It's been very impressive. But I think one thing to note here is that this success, howsoever impressive it has been on particular type of problems. Namely, these are games, mostly deterministic move games. They have large, very large state and action spaces. That's what makes them really challenging. But yeah, like I said, it's still been very impressive. But that does raise the question whether what about other kind of problems? Whether we're going to be able to make progress on other kind of problems, particularly problems coming from robotics and autonomous systems where physics matters. So here is a prototype of a very simple mobile robot. We want to be able to just have this robot walk and do various kinds of maneuvers. And this robot has states and action spaces that are both continuous. The state spaces depends on the system, but it's of the order of 30 to 35 dimensions. The action space also depends on the system, but let's say that it's something of the order of 10 dimensions. So these are not easy problems to handle for at least classical methods, including RL methods. Like I was saying, physics matters here, and one would think that one would need a model-based approach for problems like this. But given the complexity of such a system, I mean, that has proved quite difficult. Now, one thing I should say is that this is not to imply that problems of this kind are still open. So there's been work going on for quite a while on problems of this kind, and there's been progress. But increasingly, what's happening is that we are dealing with more and more sort of complicated systems that are harder to stabilize, and we are basically pushing the envelope. So surprisingly, the people have, so like I was saying, so model-based approaches have not really succeeded. So people have been trying model-free approaches. And at first, on first thought, it seems that, okay, physics matters here. So how can such approaches succeed if you ignore the physics? But surprisingly, there's been some success. But the performance can at times be fragile, and there is also some skepticism whether such approaches are really doing anything more than random search. And so that's sort of one point I wanted to make. These are mostly based on things that work on such problems. They're based on deep reinforcement learning. There is long training times, a lot of hyperparameter tuning that needs to happen, et cetera, et cetera. But the other point I want to make is that on problems of this kind, we train algorithms in a simulation using a generative model or a simulation model. This is all done offline. And so there is some value in problems of this kind, which is what this workshop is about. So I guess I don't need to convince people about that here. But that's sort of the, so this is the setting. More or less the setting of standard reinforcement learning. So there is a system with state X, action U, F is the transition function here, W is the noise, and given the current state xk and action uk and noise wk, you get the next state xk plus 1. And then there is a reward r, and then the agent takes the reward into account to determine what the next action should be. So the setting here is that we are going to assume that the transition function f is strictly speaking unknown, but we, like I said, I mean, if this is happening in a simulation, in a simulator, then we have an implementation. It just might be very complex, and we may not be able to write it down or use it in any kind of model-based approach. So the point is, so we have a black box simulator, and we can draw samples from such a simulator at will. So that's sort of the setting that we're going to consider. The focus in this talk is going to be on the infinite horizon discounted criteria. And we are interested in finding a policy that maximizes the expectation of the total discounted sum of rewards. And so we're looking for, let's say, to start with, the optimal value function V star. And of course, just one slide on stochastic control 101. We know that the optimal value function V star, it satisfies the Bellman equation, where T is the Bellman operator. So it's a fixed point of the Bellman operator. And of course, we know that T is a contraction. And so by Banach fixed point theorem, there exists such a fixed point. And then a very simple algorithm works to find it. That is, you can start with any V naught and then just iteratively apply the contractive operator on it. And then you guarantee that that will converge to the optimal value function V star. And once you have that, then from that, you can infer the optimal policy, which is what we're looking for. I mean, you want to deploy this thing, put this thing on the robot, etc. So I just want to draw attention to a little detail here. So I don't know if you guys can see my cursor. So Sean, my cursor is visible. You're muted.
Yes. Yes.
Okay. Okay. Great. Okay. I don't have a pointer. So all right. So this is in some sense this is also defining the Bellman operator, and this is the second term in the Bellman operator is an expectation of the value function, and this term is really the next state. So this expectation is with respect to next state. So that is written up here. So this is just a restatement of that, except that now we are taking into account that the next state is coming from some simulation model, or a generative model, as now it's being called. And so psi is such a simulation function. And given this state x and action u and some noise omega, psi of x u omega gives us the next state. And since the randomness is omega, then this expectation is with respect to omega. So the point of this the point I'm trying to make here is that once you make this observation, you can immediately see that you can use you can generate samples from a simulator, and you can plug those samples in place of the expectation and do a sample average approximation. And that is one very simple way of doing value iteration. All right. So like I said, so the focus of this talk is on the setting where both the state space and the action space are continuous. If the state space is continuous, and just for the for now, let's assume that the action space is finite, then we could do something like what I just said, which is just do sample average approximation inside the Bellman operator, and then you're essentially doing an empirical variant of value iteration. Something that we have studied before. It seems to work quite well numerically in many contexts. There is, of course, a problem that it still doesn't scale with the state space size. And of course, for continuous state spaces, you need to do something else. So you can combine this idea with function approximation. But there's an additional difficulty arises when you try to extend this to continuous action spaces, namely that in each iteration, you need to maximize over U, and you don't have any derivatives or anything that are available here. So it's not really possible to actually do any kind of optimization. So one possibility is that, suppose you have a compact action space, you can just take some samples and take the empirical max and plug that in, and and then you can still plug in a sample average approximation for the expectation in the Bellman operator. So that works, but it's not going to scale. And particularly when you go to higher dimensional spaces, it's not going to scale. You can do sampling in smarter ways. You can use Monte Carlo tree search type methods to do sampling. That definitely helps. But again, as you go to higher dimensional action spaces, that again runs into difficulties. So now, value iteration is, of course, only one type of dynamic programming algorithm. Policy iteration and active critic types frameworks are another. And so in the active critic architecture, which is really generalized policy iteration, so what's happening is that, and this is a very classical architecture. So what happens in such an architecture is that you introduce a function approximation architecture for the Q value function, which is not too different from the value function I was talking about so far. And you also introduce a function approximation architecture for the policy, and that's called the actor. And in a policy iteration type algorithm, you have a policy evaluation step, and then you have a policy improvement step. And now in the active critic architecture, essentially that's what you do. So you do policy evaluation, then you do policy improvement, and and you keep on going until you have convergence, if you have convergence. So maybe you might be useful to kind of just elaborate on things a bit, particularly since I will need to use some of this notation. So let's say that Q is the current Q value function that we have. Then the operator G pi is the policy evaluation operator with the fixed policy pi that that is defined like this. So it's essentially just the reward function plus gamma times expectation of the Q value function, and the action is taken according to the policy pi. So again, as I said before, there is an expectation here, and as Alex also talked about, this is a very we've been doing sample average approximation forever, so we can do that here as well. And so the policy evaluation operator will become an empirical policy evaluation operator. And it's a very simple idea. I think this is, in some sense, it can also be regarded as being unavoidable. But from an operator theoretic point of view, something interesting has happened, which is that a deterministic operator has now become a random operator. And we don't really know. And given that this is embedded in some algorithm where this is being iterated over and over again, we don't know what's going to happen. All right. So this is one sort of, so what we're going to do is we're going to use the active critic architecture. And like I was saying, both the actor and the critic, the function approximation architecture, I mean, you can pick your favorite, but they could be neural networks as well. And neural networks are universal function approximators. So, that's one attractive thing about them. But it can be hard to make, you can make things work. That's not really a problem. That is really the main thing that is attractive about neural networks. But it can be hard to prove results. So what one could do, and this is again not a new idea. I mean, these kind of ideas have been around for at least a couple of decades. So what one could do is that one could so alpha here, for example, in the policy network, the alpha here are the weights in the very last layer of the neural network, and theta represent all the other weights. And what one could do is one could pick all the other weights randomly and just only optimize over the alpha weights. And so, for example, so you have theta j. So the theta j is just one sample of the weights in all layers except the last one, and you get a number of such samples. Each such sample gives you a basis function psi of x dependent on theta j, and then you just given its the alphas in the last layer are to be determined. I mean, they're deterministic. So pi of x has such a linear function approximation form, right? And you can do the same thing on the critic side. So there is a neural network. Beta are the weights on the very last layer, and then the var theta are represent all the other weights, and then you just pick them randomly, and then qx comma u has this linear function approximation form. Except the thing to keep in mind is that these basis functions are being picked randomly. So it turns out that if you try to do this, then you can connect this to doing randomized function approximation in reproducible kernel Hilbert spaces. And reproducible kernel Hilbert spaces, I mean, they are very nice spaces to work with. They're also universal function approximators, prior to neural networks. I mean, those are the things that were in vogue, but they do have difficulty scaling up computationally. But our goal here is to both have something that is sort of computationally simple. At the same time, we would like to be able to prove that it's going to work. Okay, and I just want to emphasize, this is not a new idea. Basically, what we're doing over here is that we are putting together a number of very simple ideas that have been around or are not difficult to imagine, right? And we're basically putting them together, and we're trying to see if we can construct an algorithm that, of course, not only would like to be able to prove something about it, but that actually works. I mean, that's really the goal, that it should work. And so now let's see if we can put all the pieces together. So the first piece here is, the first step here is the policy evaluation step. And what you do is you get some samples from the product of the state and action spaces. So there are NQ such samples. And then you do the empirical policy evaluation the way I just explained to you before. You use the empirical policy evaluation. So the policy evaluation operator, and then just plug in sample average approximation from the simulations for the expectation. And then you're basically using a random operator. So that's what gives you Q hat, and you get that at these NQ points. And then after that, you just do function fitting, L2 function fitting, and that's it. And from this function fitting, you're going to get a function Q hat that is going to correspond to the policy pi k that was used to generate the actions. And of course, that's going to have this kind of linear function approximation form. So beta j times some basis functions where var theta j are random. And the thing to keep in mind is that the weights are chosen randomly in every iteration. So they are changing. They're not fixed. It's not like you choose them once and you fix them. And I think that also provides some sort of robustness, though this probably needs to be quantified. But if you somehow end up with a bad sample of thetas, in the beginning, you're not stuck with them because you are doing this in every iteration. All right. So that was the policy evaluation step. So at the end of this step, so what you have is that for a given policy, you have some evaluation of its corresponding Q value function as to how good that is. And then the second step is the policy improvement step, just like in standard policy iteration. You get samples of the state, n pi samples according to some distribution from the state space. And then this is the QK hat, the function that we just computed in the policy evaluation step. And you just plug that in here. And this thing in here is the policy that you're trying to optimize over because you want to find an improved policy. So the point is that you use the current estimate of the Q value function and try to come up with an improvement, just like you do in policy iteration. And it essentially amounts to just finding these weights alpha. So you can use some gradient descent algorithm, your favorite gradient descent algorithm to solve this. So numerically, it's all very simple. And that's it. I mean, these are the two steps in this algorithm, which we call RAND-POL. So as you can see, I mean, it involves some sampling, L2 function fitting, And that's it. And the key ingredients are an actor-critic architecture and function approximation, but with a shallow. So again, that the other thing I would like to emphasize is that we are not using a deep neural network. This is with a shallow neural network. All right. So like I said, the part of the reason for doing this is, can we prove something here? And it turns out that indeed we can. And there is, I know this is a little bit dense. There are a number of things here, but so NQ and NPi are the samples of the states and actions, something that I talked about in the 2 steps. M is the number of samples of the next state that you need in doing the sample average approximation. And JQ and JPi are the samples of the weights of the neural network for the actor network and the critic network. And turns out that if these numbers are large enough and you do enough number of iterations, then the L1 error in your Q-value function is small with high probability. And so one is able to get a non-asymptotic result, and of course it implies asymptotic convergence. So that's so that's the main result, theoretically speaking. Something that I would like to point out here is that it is universal in the sense that it's a continuous MDP. So we are going to need some regularity conditions to be able to make progress. So we need some sort of Lipschitz continuity on the transition function and the reward function, etc. But other than that, there is no assumption on the structure of the MDP that is being made. And like I said before, it is computationally quite simple. I mean, there's a lot of sampling going on here for sure, but one probably has to run gradient descent algorithm in each iteration of the algorithm, but that's pretty much it. And I have not shown the constants, but all the constants are known, and the dependence on the key parameters is shown here, and the dependence on epsilon ends up being 1 by epsilon square, which is quite typical. And then the dependence on delta is log of 1 by delta, which is also quite typical. I mean, this typically comes from the concentration inequalities that you use. And the dependence on gamma, that also is sort of, that can also be inferred here. I'm not sure if it is possible to improve upon that, but yeah, but we do have the dependence. Okay, so this is the theorem, and maybe a quick word about the proof sketch, and then I will talk about numerical performance. So actually, it turns out that the proof is not that difficult, and there's a number of steps. So first step is you just do sort of one-step analysis of policy evaluation and policy improvement, which turns out to be not difficult at all. And once you do that, then you should look at each iteration of the entire algorithm, which is the policy evaluation and the policy improvement step, as a random operator, which you can argue is probabilistically contracting in some sense. And there is a very precise sense in which which is implied. And then once you do that, then you can construct a stochastic dominance argument, in the sense that you can construct a Markov chain that will dominate the error process that you want to bound. And then the analysis just reduces to analyzing this Markov chain, and convergence and sample complexity, everything comes from that Markov chain. And the Markov chain is also very easy to construct. So there's a very natural construction of the Markov chain. So this is sort of the essence of the argument. I mean, for those of you who have seen, some of my prior work, I mean, it's some details are different, but it essentially leverages, these many of the same sort of, analytical machinery that we developed earlier, which is a nice thing. It means that it's the proof is not difficult to operationalize. All right, the big question is, does it work? So this is on the quadrupedal robot that I showed you. It's in an environment called Minitor in PyBullet. And there are 4 things that are being shown here. So the last one is this is some random search going on, and it doesn't work. I mean, that would be, at least that's what we would expect, right? That the random search is not going to work on such complicated problems. The other two are, so the one in green is something called DDPG, Deep Deterministic Policy Gradient Algorithm, which is in some sense state-of-the-art policy gradient algorithm, and it works quite well. And then the one in red is PPO, Proximal Policy Optimization, which is probably the best, deep RL algorithm for continuous control, as at least as far as we know. And the one in blue is our algorithm Rand Paul. And what you can see is that it seems to have, at least we can say that its performance is sort of comparable to PPO. And it does take more time. So computation, so it turns out that Rand Paul ends up doing, well, runtime is more for Rand Paul than for PPO. I mean, PPO is a really good algorithm, very well designed, but I think some of it has to do with the implementation as well. PPO is, very naturally uses parallelization and GPUs, so runtime is pretty fast. Whereas with Rand Paul, the code that we have, our code is pretty amateurish, as you can imagine. So I think there can be some gains that can happen by having a sort of better implementation. Okay, so this is what it looks like, but again, the question still remains: does it actually work? Before I get to that, I think just one more thing I want to say is a couple of things I want to say is that when in problems like this, what's called reward shaping is really, sometimes is the bottleneck, meaning that you want the robot to have a certain kind of, behavior or be able to do certain maneuvers. What reward function should you pick so that you can enable that? And a lot of effort is spent on that. But once you do that, then, you across algorithms, I mean, you can use that. And that's what we did over here. The other thing I want to mention here is that, Rand Paul, as you have seen, I mean, there are no hyperparameters or anything, right? It is a very natural sort of extension of multiple ideas which are well understood. And, there's no hyperparameter tuning needed. Okay, does it work? Okay, so this required about 10 to 12 hours of training, more than what PPO required. So PPO can also do this. I should not say that PPO cannot do this. DDPG is less successful, which is also evident in the plot that I showed you. But I mean, at least so this. So I think this is really the proof of the pudding is in the eating, as they say. So I think theorem and the plots about rewards and all that, I think those are irrelevant once you see this. Okay, so with that, I think I'm probably out of time. So I'll just conclude that what I presented belongs to a class of algorithms we've been calling empirical algorithms. I mean, these are really algorithms meant for learning with batch data or with generative models. These are simple. They are universal in the sense that you don't need any sort of assumptions on the structure of the model, and they have reasonably good numerical performance. They do need a generative model, so in that sense, they are a little bit far from the goal of reinforcement learning in that that you don't have you have learning complete that's fully online. So one could argue that the performance guarantees are a little bit weak because you get convergence in probability and then with high probability bounds. But once you ask for non-asymptotic performance guarantees, that's what you're going to get anyways. But they do have good numerical performance, at least comparative numerical performance. Yeah, so the ideas behind the algorithms are simple, and I think there is some hard work in the analysis, but I think once that is done, then the algorithm is pretty simple. And so this is done in what the Minotaur environment on PyBullet. So what we're trying to do now is put this on an actual quadrupedal robot. But first, we cannot do training on the on the physical robot. So we working with a colleague to train a very realistic model of the actual robot, and if it works in the simulator, then we'll put it on the physical robot. So that's what's going on right now. But it's surprising once at least for people like me who do theory, that there is such a gap between theory and trying to make something work in practice. There are multiple steps in this process, but it's a fun process. All right, thank you very much.
Awesome. Thank you, Rahul. So here's what I think we should do is, since I cut off questions for the previous speaker, I'll open up questions for either speaker, but let's give Rahul, I'll give him priority at the moment just because his slides are up and all that. So any questions? I'll open up my chat box.
Yeah, there are two questions by Gergely and Chaba in the Q&A chat box.
Oh, I'm having trouble finding it. Oh, there it is. There it is. Okay, so oh man, so Gego asks, are you doing anything fancy for exploration? Are there any issues there?
Yeah, so actually that's a very excellent point. So actually we as we're trying to translate this to to having it work on a real robot. So that's one of the challenges, because I mean, you have to be data efficient, right? And so there is an issue of exploration. So in the Minotaur, that did not come up. We did not have to do anything fancy. But as we are working with a more sophisticated model, of an actual quadrupedal robot, so we are having to do some exploration. So there is, some entropy regularization stuff that we are trying to do. Yes.
Okay, cool. And Chaba has a sequence of questions, and I'm going to start at the bottom since I had the same question about the benefit of the policy network.
Okay.
Yeah.
Sorry.
Yeah,
Let me start
with
with the first. Well, maybe I'll start with the first one. So, is there an advantage to using stochastic dominance argument over standard
yeah,
argument?
good. Okay, you go.
Yeah. So no, it is just that it just really simplifies the argument. I think otherwise it becomes just too complicated. But this is not the only way to do it. I'm sure that there are other ways of doing it. Then the bound did not show dependence on the dimension of the state and action spaces, since it was emphasized that this works no matter the MDP. Dependence will be exponential in the worst case sense. So there is definitely continuity assumption that we have to make, as I mentioned. So you need some Lipschitz continuity assumption on the transition function, or the transition probabilities, and the reward function. I think there is no explicit dependence on the dimension, but it is happening implicitly through the, through some other way, maybe the Lipschitz constants. But yeah, something we have to look at, but we haven't gotten around to kind of understanding that aspect. But as far as I can recall, there is no dependence on the dimension, but it is implicit. The dependence is implicit somewhere. Then what is the benefit of the policy network? Oh, the benefit.
Why not just kernels, for example? Yeah.
Well, I interpret this question slightly differently. So the motivation for us trying to do this was, when you want to go to continuous action spaces, and if so you can't, like I mentioned, how are you going to do that optimization, right? So one thing is you can do sampling, you can do adaptive sampling, you can try to use Monte Carlo tree search kind of things, right? But that also, we tried that. We actually have a paper prior to this, in a paper prior to this, that's what we were doing, but we could not make that work on the robot. It was just for some reason, computational scalability as well as other things, it did not work. And then we thought that maybe we just need to do function approximation for the policy also. And we decided to use neural networks. So why neural networks? So that so again, I'm not sure if I can give definitive answer like this, but I can explain the motivation, I guess. But why one, not one? Why not the other? I'm not sure I can say. prior to this, we have done function approximation, like I mentioned, in the RKHS space, and we were not able to make it scale. So again, it was not working. It was, partly a scaling issue, partly just not working on more complicated problems. And the other was computational reason, that once you put things into a neural network, you can use sort of, you can have, you don't need to program so that you can use the GPU. That was really, a key motivation actually. And then we began to think about, okay, if we're going to use neural networks, we still want to prove a theorem. How is that going to happen? And of course, we were already doing randomization of various kinds. So we thought, okay, in RKHS, when we do function approximation, again, we are using some, sampling idea and randomized function approximation. We thought, okay, why not do that here as well? So that, I don't know if this answers the question. I mean, I'm explaining my motivation. I'm saying what our motivation is. I don't know if, it is not to say that this cannot be done in another way. And our focus was very much on, at least one thing that was driving us was, what can we make that'll computationally work, both in terms of like runtime as well as it'll work, like whatever comes out, whatever policy comes out will actually work on the Minotaur robot.
Cool. So any other questions for Rahul out there?
So I have questions for, again, both Monzer and Alex, but maybe I'll start with Alex in the reverse order. So Alex, you thank you for discussing the notion of risk measures in multi-stage stochastic programming. So I think so since we didn't have enough time, so I think I still hope to get a better understanding about what's the correct notion of risk measure in multi-stage stochastic optimization. So I think I've seen papers with very different set of definitions of risk measures, some involving time consistency, some do not. So I guess my question is, in your mind, what would be the right way or the most reasonable way to think about risk measures? And also, when we define risk measures, it seems like some risk measures are defined to make analysis straightforward. But is that the way to go? Or maybe this is fundamentally just a hard question. So I just want to hear your view on this. Well, I hope he's here.
Oh, we lost him.
That's too bad.
Oh yeah. Oh, that's too bad. Yeah. Okay. Anybody else would answer that one?
No,
No.
I think he's here, and he's probably muted. So I think the host can unmute.
I just asked him to unmute.
Yeah.
But you can unmute him yourself.
Can I? I think I'm not the host then.
I cannot. I can only ask to unmute him.
I thought we were the hosts. How funny.
Yeah, also I think Mulder has dropped from the line.
Okay.
Hey Mulder, are you still there?
Send us a chat if you're there.
Okay, that's fine. Then, yeah, Rahul, do you want to answer a question?
Sure.
Yeah, about risk measures.
Sorry? Oh, risk measures.
Okay.
Well,
actually, you know something about that, yes.
Okay. So could you repeat the question?
My question is that there seems to be like a variety of definitions of risk measures for multi-stage dynamic programming, right? So I'm sure like you have seen some, and we all have seen various definitions. Do you have a sense about like what should be the right definition, or how to think about risk measures in general?
I'm not an expert, but so I can share my very limited knowledge on this topic. I think so. As you probably know that as Alex was referring to as well, right? So it started with the VAR, value at risk measure, and then CVAR. It's also called AVAR. conditional value at risk. So those are, in practice, those are kind of risk measures that are, quite, used very well. But in the last 15 or so years, there's been an attempt in particular by Alex Shapiro, and then also by other people, to develop a sort of axiomatic approach to risk. And so, I mean, it really depends on your preference. I mean, there are, you have different axioms, and then you end up with different risk measures. When you go to a dynamic setting, then I think things become a lot more difficult, because the moment you consider risk, or which is not a risk neutral measure, then the policies are going to be history dependent, right? And that really it makes things very challenging. So people have come up with the notions of dynamic risk measures and Markov risk measures and all that, but it all really depends on your application and whether those are relevant. So that's all I can say.
Mm-hmm. Oh, by the way, I think Chaba has more questions for you in the chat box, but probably we don't have time to answer them like now. Like people need a break. But
yeah, maybe, I guess.
Can you type your answers in the chat box so we can see them?
Oh, I think I answered. So I can see 3. I answered all of them.
No, there are more questions. Oh, I see.
No.
Oh, they
Maybe
will.
I didn't answer them.
Okay. Okay, cool. Yeah.
Well, there is actually one more there, but yeah. So I think we will have to take a bit of a break. So we'll return in just 12 minutes. so we just have a very brief break, and look forward to rebooting. Yeah.
All right. Thank you.
Okay.
Right. Thank you.
Thanks, Rahul. Thanks to all the speakers.